Okay, let's look back at this linearization stuff real quick. So remember, the whole point here of linearization is just coming up with a tangent line, right? We're just going to use the tangent line to model the curve close to the point of tangency. So the one equation that for this assignment that you really have to remember, the one kind of formula, would be what? Now, if we're going to call the linearization, if we call it, oops, if we call it L of x, which is really just y, right? If we're going to try to predict the output of the tangent line, what's our formula? You remember? F of a, good, plus f prime of a times dx, good. And dx, if we'd rather write it this way, whoops, you kind of take your pick here. You could also write it as f of a plus f prime of a. dx is just x minus a, right? Either way, okay? So then let's look at a couple examples where we're just going to build a tangent line and quickly try to approximate the value of a function using our linearization. So with this one here, we've got an f of x. F of x is 7 minus 3x squared, so some quadratic function. And we want to approximate the value of the function at 2.9. Well, then we want to pick a nearby convenient value, which would be 3, right? We want to plug an integer in, okay? So we differentiate. We did that last week, and we got negative 6x. So what do we got to do here to come up with a tangent line? Okay, good. So we're just going to, we need to know what f of 3 is, and that's 7 minus, what, 27? So negative 20. What's f prime of 3? Negative 18. And so that's all the ingredients we need, right, to build our linearization. So then we're just going to get L of x is equal to f of 3, so negative 20 plus negative 18 times x minus what? Minus 3. There's our line right there, okay? If we want to put this into, slope-intercept form, that just means simplify, right? So we would just distribute the negative 18, combine like terms, and we get L of x equals negative 18x. That's going to be plus 54 minus 20. Everybody agrees just that? And there's a model. There's our linear model. Now we can just plug values in. We could conveniently plug in 2.9. And this is just a line, so it's pretty easy. We don't have to do any exponentiation here, right? Negative 18 times 2.9 is not a big deal to calculate. Plus 34. I've got a picture of it here if we graph both of these at the same time. So there's our function, right? There's the linearization we came up with, is L of x. And if we graph these things, there's the function at 3, and there's our actual function at 2.9. There's our linearization. It looks pretty good, right? When we're close to the point of tangency, you can see that blue line matches up pretty well. And there's the value. We're not off by very much, okay? If we actually, let's get a more accurate value there. If I do L of, what were we doing, 2.9? So we get exactly negative 18.2. The last part of this, what do they want you to do? They want you to graph the function and the linear approximation. We wrote the equation. Estimate the given value of the function. Well, that was our negative 18.2. is what we get if we plug in our 2.9 into our line. And then the last thing is they want you to compute the percent error. Okay, so what's that mean? Percent error, it's always going to be, it always follows, you do this a lot. This is relative error. It's a percent error if we multiply by 100. And it's just relative error if we write it as a decimal. Okay? So it always looks the same way. Relative error is equal to your approximate value. Oops, can't spell approximate. Approximate value minus exact value over exact value. Okay? And they write this with absolute value bars. That's okay, but then what's going to happen if I write it with absolute value bars? Obviously, what's that ensure that my answer is always going to end up being? Positive. Okay, so we're not really concerned about the sign there. I think that's a bad idea personally, because it'd be nice to know if the relative error is, are we undershooting or overshooting? And so really a lot of times, like in physics, we won't include the absolute value bars. Now keep in mind on the assignment, they do, right? So your answer is always going to be positive. But what do we get then? So we get whatever our actual output value is, or our approximate output value is L of 2.9 minus F of 2.9 divided by F of 2.9. Rather than, like if you were doing this on Desmos or on your graphing calculator, we don't talk a lot about this in a math class, but we're getting into some applied stuff. What's the problem with just transcribing decimals there? Like I could just be plugging in decimal values, but do you see a potential issue with that? If I just calculate my output values on my TI-84 as decimals and write those in. Well, yeah, I'm getting estimations guaranteed because I'm going to have to stop unless these are terminating decimals, which they might be, but they might not be, right? I might end up having to round decimals and accumulate rounding errors. So it's always better if you can avoid having to transcribe numbers. Like if I write this in this format, even in Desmos. In Desmos, one disadvantage of Desmos, you might have noticed when you looked on that last graph, you're kind of stuck with however many decimal places it gives you, and sometimes it doesn't give you very many, right? The TI-84, you have control over that, which is nice. But on Desmos, at least I haven't figured out how to do it. If you figure out, tell me, because I don't know. But if I write it this way, it's going to give me a relative error that's, it's going to calculate this, guaranteed. Desmos is going to calculate that out to many places, even if it doesn't show me. So we can do this. If I pull up Desmos and I write that expression, so L of 2.9 minus F of 2.9 all divided by F of 2. Whoops. Look what it gives me. See, it gives me now it's giving me this calculated, this really big decimal value, and there's no rounding error there. So if I look at the answer, at the published answer, scroll down a little bit. Gosh, to 3 places we're guaranteed not to have made a mistake. Now, what's the difference here? How come theirs is 0.165 and ours is 0.00165 rounded? Well, it's because I wrote ours as a decimal. If I want to turn this into a percent error, all I've got to do is just multiply it by 100. Okay. Now, here's the other thing. Notice that theirs is positive. And it's true. The error, we are off by 0.165%. But this is better because it's telling us that the relative error is actually negative, right? This is telling us that we undershot by that much. And if I zoom in, we should be able to see that. Hang on, we overshot. Why did we get that wrong? Oh, I know why. Huh. Because that should be in absolute values. We just want to know the bottom is going to be in absolute values. Okay, we're just looking at the top not being in absolute values. And then it ends up telling us accurately that our value is that percent bigger than the initial value. Everybody see that? Now, remember, on the assignment, you're going to put absolute values around everything, right? But just for future reference, when you see this, like in a college science class or statistics class or something, just know the difference. If we don't put absolute values around the top, it's including a sign, which is useful to us, telling us if we're undershooting or overshooting. Okay, give me thumbs on that. How we doing? Okay? All right. Okay, let's try another one. Okay, try that real quick. Just work with your neighbor just quickly. See if you can set up a linearization. So we'll see if we can come up with the equation for the tangent line, the linearization. For that function, at what value are we, what's our convenient point? I mean, I wish they wouldn't give it to us, but they did. What's our convenient value we're choosing? Our point of tangency is going to be at x equals 0. Yeah, because negative 0.03 is very close to 0, which is an easily calculable output. Okay, so try that. How'd we do? Did we get it? Let's take a look. Okay, so we're going to need a derivative, aren't we? What's our derivative function here? Okay, everybody give me thumbs up. Everybody agree? Okay, good, good. Our convenient place is 8, right? So then we're going to do, when we write or a equals 0, sorry. When we do our linearization then, we're going to be doing f of 0, right, minus f prime of 0 times x minus 0, right? So what is that? What f of 0 is what? What's e to the 0? What's anything to the 0? 1, okay. So we're just getting 2 times 1 over 1, so I get 2. And here I'm going to get negative 2 times 1, so minus 2 times x minus 0. There it is, right? There's our linearization. Okay, and we just want to know, we want to approximate what the value of the function is at negative 0.03. Okay, so negative times negative is positive. So what's it going to give us then? Linearization is 2.06. That good? Good? That what everybody got? Okay.
Wait, if you're putting a negative in, why didn't you put the negative on the right side of the equation?
This line right here?
No, like, it says to input 2e to the negative 0.03, right?
Inputting that, right? Negative 0.03.
So you don't have to include the negative?
Where, you mean right here, you mean?
Yeah.
Oh, okay, yeah, I did, but I shouldn't have done it the way I did. Look at our equation above. This is, see what I'm saying? That's negative. So when that becomes negative, this just turns into, I should have shown that. This just turns into positives. Yeah. Okay. All right, so then if we wanted to compute our percent error. Now there's another way we can also approach this. Like what if, well, I'm not going to do that right now. We'll wait till we get to differentials. Okay, so if we want to compute our percent error then, you remember what the formula is for percent error? Approximate minus, so there we go. So relative error would be approximate, which is going to be our L, right? That's our approximation. So L of negative 0.03 minus f of, good, we want the exact value, divided by absolute value of, okay, and if we look at this on our graph, I just happen to have a little trusty graph of this. Thought I did. How come it's not showing up? Oh, well, I got it over here. Okay, there it is. There's our function, e to the negative 2x. There's our linearization. You can see that close to 0, it's a good approximation. So let's do f of, sorry, negative 0.03, comma, f of negative 0.003. So there's the actual point. There's the linearization. They're pretty close, right? And if we zoom in, we can see that we undershot a little bit, right? So when we come down, and we should expect to get a negative relative error when we do this calculation. And we do. Okay, everybody see that? But remember, of course, for us, and we're going to multiply by 100 to make it a percent. And then for us, we'd make it positive, right, on your answer.